Greetings, calculus students. So in this next section, we are going to be learning this massive theorem, which is called the fundamental theorem of calculus. It's a very serious name, and it's just a theorem that is dealing with integrals, which we're learning about right now. So far, we've learned about two really big different branches of calculus, and those have been differentiation and integration, okay? And even though these might not seem very similar, since differentiation is all about finding slopes and tangent lines, and integration is all about finding the areas under curves, they are actually very related. And it was someone named Isaac Barrow who discovered that these processes are inverse operations, okay? So that makes sense. Based on what we've learned so far about inverses, we've learned that it requires something called anti-differentiation. And so anti-differentiation is like the inverse of differentiation. And so derivatives and integration, it turns out, really are inverse operations of each other, okay? And so the way that this inverse relationship shows up is in what's called the fundamental theorem of calculus. And this video is going to focus on the fundamental theorem of calculus part 1, because there are two parts. So this is just the fundamental theorem of calculus part 1. And to make this a little bit shorter, we can always just say that this is the FTC. So fundamental theorem of calculus is the FTC, and this is FTC part 1, okay? Which is what that says. Well, I'm going to say FTC part 1. All right. And so what this theorem tells us is that if we have a definite integral, so definite integral is when we're given values right here. If we are not given values a and b, then it is an indefinite integral. But this theorem is applying to a definite integral, so we have values a and b. Then mathematically what this looks like is that we take big F and evaluate it from A to B, which means we find F of B and then subtract F of A. So we've kind of learned how to solve a definite integral mathematically with this equation. Graphically, what this is looking like is I have a function F. There's my F. And so from A to B, what we're doing is we're finding this area here, but only between A and B. So basically we would find from negative infinity to infinity to B, and then we're essentially shaving off all the parts that are in front of A, right? And so that's why we do F of B minus F of A. So we're getting rid of all the extra part that is in front of A. So everything in here is F of X. Okay, that's my big F of X from A to B. All right, and so mathematically, this is what the fundamental theorem of calculus part 1 looks like. All right. So what is in here, inside my integrand, is my f of x. So my fundamental theorem of calculus says I need to find big F of 3 minus big F of 1, all right? So if f of x is e to the x minus 3, then big F is going to be e to the x. That's the antiderivative of e to the x. And the antiderivative of minus 3 is minus 3x, and I'm evaluating from 1 to 3. So I basically did this step right here, and now I'm going to rewrite it like that. So this is equal to e to the 3 minus 3 times 3 minus e to the first power minus 3 times 1. So that is this last step. And now I can just simplify. So here I will get e cubed minus 9 minus e. Gotta make sure to distribute this negative sign to both things inside the parentheses. That's why the parentheses here are so important. this becomes positive 3. So this is e cubed minus e minus 6. And we can just leave our answer like that. So we just applied the fundamental theorem of calculus. Woohoo! All right. Let's try B. So we're gonna rewrite it this way first. I have little f right here, and I need to figure out what's big F. So this is one of my inverse trigs. You should start recognizing the inverse trig so you don't get confused when they come up. If you look back at your table for antiderivatives, this is the inverse trig. 2 is my constant, and this is inverse sine. So that's my big F, and I'm evaluating this from 0 to 1/2. And now I will rewrite it like this: big F of B minus big F of A. So I will plug in 1/2 first, and then subtract 2 minus sine of, oops, I'm doing my notation completely wrong. I'm supposed to write inverse sine just with a -1. Inverse sine is -1, and plug in 0. So I've got to remember my inverse trig. Inverse sine just goes for these values. So where sine equals 1/2 is right here at pi over 6, and sine equals 0 right here at 0. So those are the solutions to the inverse trig problem. This equals 2 times pi over 6 minus 2 times 0, which equals pi over 3. Finally, one last problem to do together. I'm going to rewrite this thing. Usually we like when we rewrite it as an exponent, but I know that when I have an exponent of -1, I'm not actually going to be able to use the power rule. It's better when I rewrite it like this because the antiderivative of 1 over x is ln. So this isn't one where I'm going to use the opposite of the power rule. The antiderivative is ln. So this is ln of x from 1 to e squared, a to b. And then I can rewrite this as ln of e squared minus ln of 1. Here I have to remember some properties of ln and logs. So whenever I have a power inside of my argument, I can bring the power out like this. Ln of 1 is 0. And the reason why I wanted to bring the power out in this case is because ln of e they cancel each other out. That's 1. So this is 2 times 1, which is 2. Okay, so I used a lot of properties of logs right here. If you got confused, I guess look up your properties of logs again. All right. So that's how you apply the FTC Part 1. I want you to try, I know this problem looks super duper intimidating, but this is similar to the other problems that we did. Basically, you just have 3 different indefinite integrals. So you could split this up into 3 different indefinite integrals and apply the fundamental theorem of calculus just like we did right here. So I want you to try this one totally on your own. And the last thing that I'm going to show you in this video is down here. So in this paragraph, it says, just as we can use areas of regions to help us find definite integrals, now that we officially know how to evaluate definite integrals, we can use integrals to help us find area. So we're going to be finding area again, but this time finding areas of things that are different from like a rectangle or a triangle. So we're going to find areas actually using definite integrals. Okay, but we have to use caution because we know area is always positive, right? We know this, area is positive, and we're responsible for making negative regions positive, okay? So we need to identify what are our positive regions, and more importantly, we need to identify what are our negative regions so that we can turn them positive. So to do that, we do have to know what these graphs look like, okay? So here's my equation. I'm gonna start off just by sketching this. So this one's really easy. It's just a parabola that's been shifted down 1. So a quick sketch will look like this. And then this goes all the way to 3. So it's gonna be something like this. I'll do a different color, blue. Something like that. It's not perfect. What's actually important that I know is my x-intercepts. So I really just have to know my x-intercepts. If you, well, I'll show you another strategy in the next problem, okay? So there's my x-intercept, and I'm solving this from 0 to 3. So I want to find this area right here. Whoop, and then up there. Okay, so it's important that I identify my negative integrals. I can see one of them is right here. And what I'm going to do with this negative integral is we have to make negative definite integrals positive area. Okay, so I'll make a note of that. We have to make negative definite integrals positive because area is positive, right? So the reason why we're doing that is just because the problem is asking me about area, right? So here it says find the area bounded by that parabola. If this wasn't asking me for area, if it were just asking me for the definite integral, I wouldn't have to do this extra work. I would just take the definite integral. But because this is area, I have to do this extra step, and I have to make that definite integral positive. So basically, this is at the point 1, 0. So I know that the definite integral from 0 to 1 will end up being negative, and I have to make it positive by adding a negative sign in the front. So this is the extra step we have to do, okay? And then we're going to add it together with the definite integral from 1 to 3, and we can just leave that normal because I know that definite integral is going to be positive, okay? So that's the step that we have to take. And then we just solve this out the same way that we were. We just have to be careful with our negative signs. So the antiderivative of x squared minus 1 is 1/3 x cubed minus x. I'm evaluating that from 0 to 1 plus 1/3 x cubed minus x, and I'm evaluating from 1 to 3. Here's where we've got to be especially careful with our parentheses. There's going to be a lot of parentheses going on. So I'll plug in 1. I get 1/3 minus 1. Plug in 0. I get 0. And now I plug in 3. I get 27/3 minus 3. And then plug in 1. I get 1/3 minus 1. I'll distribute all my negative signs. This is negative 1/3 plus 1. Over here, 27/3 is just 9. So this is plus 6 minus 1/3 plus 1. So combining like terms, I get 8 minus 2/3, which if I combine those together, I get 22/3. Woohoo! That's without a calculator. So without a calculator, I really had to do all this extra work to figure out where is this integral negative. And then I had to fix it by putting a little negative sign in the front. If I have a calculator, I can just type this into the calculator. area, I'd say just take me the definite integral from 0 to 3, but in order for the calculator to make it positive, you would put it into absolute value bars, like so. Oopsies. X squared minus 1 dx. So you would make sure to use these absolute value bars on your calculators whenever you're finding area. And it gives you the same thing, 22/3. Voila. So down here again, we're supposed to find the area of this equation. This equation is a little harder to graph, I'll be honest. So if you don't know the graph so easily, it's okay. Really, we just have to figure out what our x-intercepts are, okay? So we have to find our x-intercepts and then determine where the graph is positive or negative. So to find an x-intercept, I'm just looking to see where the function is equal to 0. Like if I look up at this graph, I was just seeing where my function, where the y value equaled 0. And so I can do the same thing here. I can just say, all right, where does this thing equal 0? And then solve. So here I'd get 2 over x equals 1. Cross multiply, or I get x equals 2. And then I'll just make a little table to figure out if this is my y. I'm looking between 1 and e, because that's my interval values, between 1 and e. 2 is right about there. And then I'll just figure out where is this function positive or negative. So if I plug in 1.5 into my original function, so I'm just plugging it in here. If I plug in 1.5, I end up with a positive number. And if I plug in anything bigger than 2, I'll get a negative number. So I know that my integral is positive right here, and it is negative right there. So when I'm doing my integration, I need to put a negative sign in front of the integral from 2 to e. Okay? So that's how I will set this up without a calculator. I can just go from 1 to 2 normally, since that's nice and positive. But then I have to subtract and put a negative sign in front of the integral from 2 to e, since that is a negative value there. Okay, and then we're just applying the fundamental theorem of calculus, the same as we just did. So the antiderivative, our big F, is 2 ln of x minus x from 1 to 2, minus the same thing, 2 ln of x minus x from, oops, but this time I'm going from 2 to e. Keep applying the FTC. Be careful with our parentheses. So I have 2 ln of 2 minus 2, minus 2 ln of 1 minus 1, then minus, here's this minus sign, 2 ln of e minus e, minus 2 ln of 2 minus 2. Okay. Do a little bit of algebra. I'll let you try that on your own. In the end, we get this weird value that I probably could plug into a calculator to get a decimal, but that's what you get when you simplify. Okay. On a calculator, it's very similar to up here. Go ahead and pause me and put forth a guess of what you think I'd type into the calculator. Beat me to it. Pause me and put a guess. So hopefully your guess looks like this. The area would be the integral from 1 to e. I'm not going to worry about the different bounds because I'll just take the absolute value of 2 over x minus 1 dx. So that's it. That's all the problems that we have to think about with dealing with our fundamental theorem of calculus part 1.